Hello everyone. Today we'll talk about the BCD and Ascii operands and instructions in microprocessor course, chapter 3, section 3.4. In 8086 microprocessors, there are many instructions that handle ASCII and BCD numbers. This section we will talk about these instructions and we will take some examples about it. Let's start with BCD number. The BCD number is needed because the people usually use the digits from 0 to 9. This digit, the people use it from 0 to 9, and this digits is represented by BCD numbers as following the table: 0 as 000 and 1 is 0001 and so on. And we have two types for BCD. The first one is unpacked BCD. The unpacked BCD, the lower 4 bits of the number represent the BCD number and the rest of the bits are 0. So if we take the examples in here, the 0 is 0000, the lower 4 bits, and the upper 4 bits it's become here, and also it becomes 0000. And for example, for 5, the lower 4 bits, the 0101, and the upper 4 bits is always 0 in unpacked BCD. And for backed BCD, in unpacked BCD, a single byte has two BCD numbers in it. One in the lower 4 bits and one in the upper 4 bits. For example, if we come back to this table, for example, is to 0010 in lower 4 bits, and the upper 4 bits it becomes 0000. If we have 59 in decimal number, how we can represent it to binary number or in back BCD? 5 is 0101 and 9 is 11001. This is the back BCD number for 59 in decimal number, and like this we can obtain the back BCD. Let's continue. ASCII number. The ASCII number, computers can only understand the numbers. So an ASCII code is the numerical representation of a character, such as the alphabet or numbers. For example, here the 0 is represented by ASCII code is 30, and in binary 0000, as we showed before. And for 1 is 31, so we start always from 30 and so on. For the numbers and characters, there are many ASCII codes for them. Now if we want to convert from ASCII to BCD, first the ASCII data provided by the keyboard must be converted to BCD. Whether it should convert it to backed or unbacked BCD depends on the instructions to be used. There are instructions require that data in unbacked BCD, and there are instructions that must have backed BCD data to work properly. And we'll take some example to get more understand. So here we have ASCII to BCD conversion. We have two types, as we learned before: one to unbacked and to backed BCD. Now we will learn how to convert ASCII to unbacked. To convert ASCII to unbacked, BCD must get the right of the tag 011 in the higher 4 bits of the ASCII. To do that, each ASCII number is ANDed with 00011111. So let's run this program and we will see how to work and how to convert the ASCII code to unpacked BCD. To run this program, we have to use DOSBox or emulator 8086. I will use DOSBox now, and as we see now here our code is running with the loop. Now in here we have this our ASCII code, and here the unpacked BCD converted. If you see here, it's take 2 by 2, and it's running also 2 by 2 in register, and like this we can convert it. And now for the second type, ASCII to back BCD. To convert to back BCD, first we have to convert it to unback BCD, then combine to make back BCD. In here we have the key 4 and the key 7. The key 4 in ASCII that is the 34, and the key 7 is in ASCII 37. If we convert these two ASCII codes in unback, we will get the 000 and 0100 for key 4, and we'll get 0000 and 0111 for key 7. If we combine these numbers, we'll get the number 47 in back BCD as following: 0100 is the key 4 and 0111 as key 7, and like this. Now we will learn how to convert back BCD to ASCII. To convert back BCD to ASCII, we'll take the reverse of ASCII to back. First, we have to convert from back to unback, then to convert from unback to ASCII code. As shown in this example, we have the back BCD 29 as follows: 001042 and 100149. In unback BCD, we take it as separately. 42 is 000 for upper 4 bits, and 0010 for lower 4 bits for 2. And for 9, always we know that the upper 4 bits is 0, so we have to, for 9 in lower 4 bits is 1001. Now we have to convert the unback BCD to ASCII code. It's like this: 2 in ASCII code is 32 as represented by 0010, and is it 32 in ASCII, and 39 in represent the 9 in unback BCD, and like this. Now I will run this program to see how it's the converting work from ASCII code to back BCD number. As you can see here, the converted from 4 and 7 key to the ASCII code number. This is the 4 key, and this is the 7 key in ASCII code, and this is the 47 in back BCD, and like this. Now we'll talk about the BCD addition and correction. In here there is a problem. When add two numbers in BCD, must the result be BCD numbers, otherwise not correct. How to solve this problem? If we have the result is not BCD numbers, we have two options. One option is if the adding give us like this one: 0011 and 111p. This one is not BCD number. how to make it BCD number and correct result by adding 6 to the lower byte. If we add 6 to the lower byte here, 3 and F, will get what? We'll get 45. And 17 plus 28 is equal to 45. In, in other hand, if we have, for example, 52 and 87, it's equal to D9. And D9 also, it's not BCD number. Also, to solve this problem, we have to add 6 to the upper digit. So if we add D9 plus 60, 60 here, we have to add D9 plus 60, it's equal to 139. If we add 52 and 87, we'll get the 139 in BCD. And we have the DAA, this correction, this problem. So in program, if we have this problem in program, the DAA is correction it. So the DAA is must to add 6 to lower byte if we have to lower byte is needed if it's need, or 6 to upper bound is need. For example, let's run this program and to see how those two numbers adding each other. By running this program, we'll see now how to add these two BCD numbers, 47 and 25. As you can see, 47 the first number and 25 the second number, and 72 is the addition. Okay, now we'll talk about the BCD subtraction and correction. As we learned before in the BCD addition, after the summation to BCD numbers, if we have in the lower four bits greater than 9, we will add 6 in the lower four bits, and also in the upper four bits, if we have greater than 9, we will add 6 to upper four bits to solve the problem. And here we have the same problem, but here we have the instruction DAS to solve this problem, and we can see this program, and we will see how this DAS solve this problem, and we will see also the result of subtraction to these numbers. And here, after the running program, as you can see here, the first number is 8, 79, 65, 14, and 10, and 12. And the second number is 3, 16, 10, 64, and 03, and 92. And here we have the result after the subtractions. With also the DAS solve all the problems in the subtractions. As you can see, this is the result: 5, 63, 54, and 56, and 20. And like this, we can subtract two BCD numbers. Okay, now we'll talk about the Ascii addition and subtraction. Ascii numbers can be used as operands in add and subtract instructions the way they are. In here we have instructions AAA and AAS to solve the addition and the subtraction problem. AAA to addition problem and AAS to subtraction problem. In the addition, if we have in the result in the value of greater than 9, AA will correct it and pass the extra bit to carry and add 1 to AH. And let's run this program and see how we can add two ASCII numbers. As you can see here, the first number is 5, and in ASCII is 35. The second number is 2, uh, in ASCII is 32. As you can see here, the same. And this AAL instruction will change any, if we have any, if you have the value of, if we have the value more than 9, AA will correct it and pass the extra bit to carry and add 1 to AH. Let's see. As we can see here, as we can see, the result is 67, and the AAA change it to 07, and like this. And let us run also this program and see also what will happen. As you can see here, subtract AH and AH as in the program. The next step, move AL to 7, and 7 in ASCII is 37. Move BL 5, and as we learn, 5 is 35 in ASCII code. Now add AL and BL, and now the AAA will correct the all problems if we have, and this our result. As you know, this our result, 6C, as you can see here, 6C after the solving problem. T-link is 5.obj, debug the program, exe. As you can see here, 0105, the first number. We move CL to 06, subtract AL and CL, and here ES, AS to solve any problem if we have. As we can see here, the result is FF and converted to 09. As you can see here, this our result, 0009, and so on, like this. The AAS correction, the any problem we have in subtraction. And now we have two facts must we know. First, A and AS just work on the AL register, and the second, the data added can be unpacked BCD rather than ASCII, and AA and AS will work fine, otherwise no. And now let's run this program and see how to add two ASCII numbers and convert it to unpacked BCD. Here we load the file in the program. AAM. As you can see, we don't have any errors. Debug the program, and we can see how the program works. Here our registers in the first step in the program here move, as you can see, move DS and AX, as you can see here, and now AX 06. As you can see here, the first number is 0659478127, and here the first one, and the second one 0779563678, and the addition of those numbers we have in here. This is the result after the adding 1439041805, and this number in MBAG BCD is here, the result 1 and 439041805, and like this. We can add two ASCII numbers and convert it to MBAG BCD. Now we'll talk about the MBAG BCD multiplication and division. In this type, there are two instructions designed specifically for multiplication and division of MBAG BCD operands: AAM and AAD. AAM for multiplication and AAD for division. AAM, if we have two numbers in ASCII code, it's converted to BCD number and multiply them, and also convert the result to BCD number. This is what AAM work. Let's run this program and we will see how it's work and how the AAM converted to BCD. T-link and debug the program. As you can see here, 7 and 37, move 37 in ASCII, and AL0F 36 as X as 6, and DL0F DL multiplication. AM here to solve the problem which we have, and to convert the BCD number. As you can see here, the result 0402 in BCD number, in MBAG BCD number, and the result of multiplication 0 by 6. And also here the result of the result of multiplication in ASCII code, and so on like this. Yalla, bye bye.